是内测用户那里那个 Chat GPT 拿来网用啊，网一网，现在不是用不了了吗？为什么又用不了？去工作呀，收费又关了，那收费呢？收费是有收费的诶，去等一下，对这两个比例这是什么？这向量是可以的。什么向量或者什么？B1 B2是向量还是标量？它上面写的是向量，但我感觉在这一空里应该就是个标量。我最好换掉哈。不是？所以它是向量还是标量？变量。变量。嗯，那上面觉得比较好把它换掉。其实那两个没有关系，就是他们没有关系，还是我把它变成这个是新的东西，没关系的。这样的语言它包含在那里面，这样的语言，嗯哼，它包含在看你怎么选。二方里面是什么啊？二方里面是二方里面就是两个数吧？哎，记得我们上学期学标量，两个 t 不吧？是有序数对 order 的法对对，那它怎么会变成矩阵的形式？就看你怎么表示它哦，看你怎么表示，看你怎样表示它。你可以写括号符，我也可以写括号符，也可以写括号符。那这里的 b 标都是标量，变量啊，所以这里其实是标量。嗯嗯嗯嗯。 别推什么？对你 drop 掉另外一个数学，就你 drop 掉另外一个。对吗？啊？ Hello, testing, 1, 2.
可以share那个题吗？因为我那边看不到那个字幕。
share 那个 Teams，
去，
还是要关灯，也是看不到。
我过来这边。
Hello, testing. Can everyone see the screen or not? You need to turn off the light. Everyone can see it from the back. Can you see? Yeah. Okay. Okay. Good. Afternoon. Be Valentine to all. Okay, we got new students still coming in. So tomorrow we have quizzes. You have quiz on topic 1 up to linear transformation, 1-2 and 1-1. Okay. So let us recap. Yeah. I want to come to the lecture. What's the cat doing? Okay, if it is disturbing, can bring it up later. Okay. Okay. So last lecture, at the end of the last lecture, there's one student come and ask me how to prove one-to-one, prove or disprove one-to-one or onto. Okay. So today, before we start lecture, we will address this question first. So let us recap what we did the whole week last week. So the central objects we deal with is the momentum matrix. Okay. So for example, let's look at a 2x2 case. Okay. And an momentum matrix is equivalent to a linear system, okay, where we want to find the solution set to a system of linear equation. For example, we have such linear system building up using the matrix entry. And it's also equivalent to a vector equation where we split the matrix into columns vector. So x1 times a1, x2 times a2 equals to the vector b. And equivalently, we have a matrix equation. So we assemble the column vector into a matrix and then multiply the solutions vector equal to the constant vector. Okay, so these three is a different incarnation of the same mathematical objects. Okay, and actually the real beast that we want to study is linear transformation. In this case, it will correspond to a transformation from R2 to R2 because it's a 2x2 matrices. Okay, where the first one is the domain. We have a map from a domain to a codomain. Okay, so given a linear transformation, you should be able to find the associated matrix. Okay, so how to find the associated matrix? So you should let your T act on the standard basis. In this case, is E1 and E2. Okay, which is the E1 and E2. Okay, up to now, okay. So, yeah, okay. So we have a function. Okay, so the natural question to ask is whether this function is one-to-one or onto. One-to-one or onto. So let's put down one-to-one onto first. Okay. So for every we don't use this. So for any b in your, sorry, let me start from a linear transformation first. Let T be a linear transformation from Rn to Rm. Okay. So linear transformation satisfy two property such that it preserves the vector addition and scalar multiplication. Okay. So okay. So what's onto? So for every b, yeah, don't use this notation. For all b in the codomain, okay, for all b in the codomain, we have at least one x in the domain such that ex equal to b. Okay, so how about one-to-one? One-to-one is for all. Also, you look at everything in the codomain, okay, but we have only at most one x in the domain such that x is equal to b. Okay, so in your mind, okay, in your mind, you can think of the onto function as you can map everything into the codomain. You map to everyone in the codomain. Okay, let me draw it a bit nicer. Readable. Maybe I draw it deeper. Okay, let's say we have 3, and then we have 3 here. Okay, so everything get mapped. Everything in the codomain get mapped by the element in the domain. Okay, but one-to-one, maybe you have more things here, and then you can map to the same thing. Okay, but one-to-one, you could have at most one mapping from the domain. Okay, you also could have nothing mapped to the codomain. Also one. Okay, so onto and one-to-one. Okay, so let's go to the back. Okay. Yeah. Okay. So the key here is this at least one and at most one. Okay. At least one and at most one. At least one, at most one. Okay. So practically how you check it. Okay. So
practically how you check it. Okay, so like we said just now, okay, so Tx equal to B. Okay. If you found the, okay, let me lay out the strategy. Okay, so let's compare again. So at least one and most one of the solution set. Okay, so in the end, you still need to look at the this equation here. Okay, bring it here. Okay, so study the equation Ex equal to B. Okay, for all B. Okay, so the key here is for all B, arbitrary B. Okay, so you can write it in variable form. Okay? Depend on what's the m here. Okay. Yeah. Depend on the codomain of your linear transformation. Okay, so we know that we can find the associated matrix A to T. Okay, so that we can turn this equation into a matrix equation, right? Okay, such that AX equal to B. Okay, so from here we want to find the solution, become a question to solve the augmented matrix again. Okay, so solve the augmented. So solving the augmented matrix, how many how many situations you will get? Either the system is consistent or either the system is inconsistent. Okay, so either consistent, either inconsistent. So consistent, what does it mean by consistent? How many solutions you have? Okay, one solution. Okay, I cannot say one solution. It should be the only one solution. Okay, there's only one. Only one solution, or there are infinitely many. Okay, inconsistent meaning no solution. Okay, good. So only one solution meaning it is one-to-one or onto. There's only one that map to that B. So the system is one-to-one. Okay. So infinitely many onto. Okay, it's not one-to-one because there are more than one element that get mapped to the same element. No solution meaning, meaning what? No solution get mapped to the B, to any B. So you cannot hit everything in the codomain. So it is not onto. Okay. So from here you didn't see not one-to-one, right? Okay. Actually here is not onto, but not onto. Okay, because you have many solutions that map to the same solution. Okay. Any question up to here? Any question up to here? Any question? Not onto. Oh, what does not onto mean? Okay. So what does not onto mean? Okay, so maybe let's start from what is onto. Okay. So repeat again, what's the definition of onto? So for every okay, ERN to RM is onto if for any B in the codomain find at least one X in the domain such that Tx equal to B. Okay, so onto mean I can hit to everything in the codomain, right? So what is not onto? So what's not onto? He is not onto be written if there exists one element in the codomain such that no X in the domain get mapped to the element in that the specific element in the codomain. So there's one thing in the codomain that I cannot map to. Okay, it's like the picture here. So this picture here is not onto. Okay, because there's one thing in the codomain such that there's no element in the domain get mapped to. Okay, not onto. Okay, so yeah. Okay. So that means if you want to show something is not onto, you need to find a B such that the system is inconsistent. Okay, you need to find a B such that the system is inconsistent. Any question? Yeah. If it is not onto, then it must be one to one. Nope. Okay, because I can have something like this, not on two and also not one to one. Okay, so what can I do? I can do like this, 3, 4, this, like this. Okay, not onto. Is it? Maybe I make it bigger. So let me redraw this line here. So this one get mapped to here, get mapped to the same one. But it's not onto because you don't hit to all the elements in the codomain. It's not one to one because you have two different elements get mapped to the same. Okay. It could be that not onto and not onto.
Which solution?
Which solution is this? Okay, which solution is this? Okay, good question. So what kind of augmented matrix you expect for this case? Okay, let's bring it up. Okay, what kind of solution you expect from here? Okay, so not onto. Okay, let's deal with the first one. Okay, so not onto meaning meaning what? Let's bring this over again so that we remember what we say. Okay, so not onto meaning there's B such that the system is inconsistent, right? Okay, so you need to find a B, B1, B2, up to Bm, okay, such that you could have a row of 0 or more than one row of 0, such that you have a inconsistent system, making the seems like I write like this a bit bad, because okay, make sure BM is not 0. Okay, so if it is not onto, meaning you can find one vector in the codomain. My codomain is what? BM, right? Okay, so it's BM, such that when you row reduce it, okay, you could have a row of 0. Okay, how many row depends, but at least one row of 0. Make sense? 0, 0, 0, and then something non-zero. So you have a inconsistent system. Okay. And how about not one-to-one happen in the same time? Okay. Not one-to-one meaning this system should have at least one free variable. Right? Okay. So this means not every column has a pivot. Okay. So let me make it a bit. So not every column have a pivot. Okay. So maybe you have this such that S3 is free. Okay. So let me move things up. Okay. So this means the system has at least one free variable, meaning not every column is a pivot column. Okay. So maybe I give you an small dimensional example here. Okay. Not onto and not one-to-one. Okay. So maybe we can consider something big in the codomain. So let's look at R2 code P. Is this big enough to see? Okay, I think this is big enough to see. So something is not onto one and onto will be this map here. So just let the associated matrix be 1, 0, 0, 0, and 0, 0. Okay. So this case here, this is not onto and also not one-to-one. Okay. Why is it not onto? Because if you explaining this, okay, so why is it not onto? If you look at the augmented matrix 0, 0, 0, and then 0, 1, 1. Okay, so this is inconsistent. Okay. Because you only need to find one B in the codomain such that the system is inconsistent. And how about not one-to-one? Why is it not one-to-one? Maybe you can tell me why is it not one-to-one? Can you find two vectors that map to the same? Yeah. What? Yeah, free variable. Yeah, correct. Pivot. Yes. Okay. So S2 is free. Okay, S2 is free. So in particular, so if you solve the homogeneous system, right? Okay, you have x1 is 0, s2 is 3. Okay, what does this tell you? Okay, so if you set okay, maybe I write a bit more. So the solution to the later we will see again this concept here. A bit small, is it? Please let me know if a bit small. So if you look at the solution to the homogeneous system, okay, you have 0 and S2 here. Okay, what does this mean? Anything you sub into S2, okay, this whole vector will get sent to 0 by this matrix. So 0, 0 gets sent to 0 by this matrix. 0, 1 also gets sent to 0 by this matrix. 0, 3, 0, 4, 0, anything gets sent to the 0 matrix, 0 vector. Okay, so it's not 1-to-1 because there's more than one x that gets sent to 0 by this matrix. Make sense? Okay. Any more question? Any more question? So let me just spell out what I just said. How about let me just write out what I said just now. Not 1-to-1. For 0 vector in the codomain, in this case R3, we have T 0, 0 equal to 0, 0, and also T 0, 1 is equal to 0, 0. Because in particular, okay, not 1-to-1, you just need to find a B such that there's more than one that gets sent to the same B. Okay. Any more question? Is it 3D? Any more question? No? No? Yeah, tomorrow test will be up to this section, 1-to-1 and 1-to. Okay, no more question. So we will continue from the last lecture. Okay, where did we stop? From the last lecture. So last lecture, we write the elementary row operation as matrices, okay, which we call the elementary matrices. Okay, just to recall that these three examples here. So E1, okay. So if you compare to the identity matrix, which did nothing to matrix, if you put a -4 in the off diagonal entry, what happens? Okay, so it depends on where you put it. And if you put 4 on the, this is the what's entry here? A31 here. Okay, so if you place at the A31 here, what happened? You will take -4 row 1 plus row 3. Okay, this is what we verified last time. This one here. Okay, -4 R1 plus R3. Okay, so actually we should write in the other way so that we know which row get replaced. So R3 -4 R1. Okay, so we know that R3 get replaced. And then E2, what happened? E2, if you compare to the identity matrix, you will see that is the identity matrix, the second row and the third row swap. Okay, so what it does to the matrix is you swap the second and the third row. And then E3, what does E3 do? If you change the diagonal entries, okay, depend on which row you change, it will scale that row. Okay, if you change the last row, you will scale the last row. Okay, this is just recall what we did last time. So, so this means that if you do row reduction, what you actually doing is you applying a matrix to your original matrix. Okay, get it? So you are actually applying matrix to row reduct your original matrix. Okay. So row reduction algorithm is actually a sequence of matrix multiplication. Make sense? Must make sense of this part, otherwise you won't make sense of the inverse identity part. Anyone cannot get this part? Row reduction algorithm, the 3-step, what you really do to the matrix is you are multiplying elementary matrix to the original matrix. Okay? Make sense, everyone? Okay. Okay. So what I draw last time is if you have a elementary row matrix, elementary row operations on the matrix, okay, like this, okay, then you can see it as a sequence of matrix multiplication. Okay, you are actually multiplying this matrix on it, or maybe let me label it EI, EJ, EM. Okay, maybe you will notice that why the direction go here, but our direction is going here. Okay, because you are doing EI first on the matrix, and then EJ, and then EM. Okay, that's why the order is a bit different. Okay, so once you do the row reduction, okay, row reduction until you reach REF, the reduced row echelon form. Okay, the theorem is if a square matrix is invertible if and only if it is row equivalent to IN, to the identity matrix. So if and only if the reduced row echelon form of a matrix is identity matrix, then A is invertible. Okay, what does it mean to be invertible? There exists an A inverse such that AA inverse is equal to identity. And also A inverse A is also equal to identity, right? So why is this true? Okay, why is this true? Okay, so the given information is what? It is row equivalent to identity matrix. This means if you do the row reduction step, okay, for finitely many steps, and then what you get is the identity matrix. Okay, so can you see the similarity between this equation and this equation here? Okay, you have something multiplied to A, which is the identity, right? Okay, in fact, the composition of the elementary matrix from the row reduction algorithm is your A inverse in this case here. Okay, so this is the claim. Okay, this is okay. So any question? This is what we mentioned last week. Any question about this? Any question about this? No? Okay. If no, let's see examples. Okay? Let's see examples. Let's see examples. Okay. So suppose we want to find the inverse of this matrix. Okay. I think I bet there's no enough space for this. So let's copy this part out. 014 and 103. Okay, so find the inverse of this matrix. Find the inverse. Okay, so can we row reduce this to an identity matrix or not? Okay, we must. Okay, we must because we want to find the inverse. So what you can do is you can set up this matrix here together with an identity matrix. Okay. So the claim is after you roll, okay, so you will do the step here is let me write down. The step is row reduct, row reduct, row use A into identity matrix, and apply the same step to the identity matrix on the left, on the right, sorry. Then, so let me label this as A. Then this momentum matrix, the big momentum matrix, will get transformed to I and I inverse. Okay, right? Okay. Okay. And yeah, no question, then let's do it. Okay. So let's row reduce this. Okay. So what will I do is I will interchange R1 and R2 first so that I get the pivot on the first entry A11, the same to the second guy. Okay. And then I make everything below the pivot position 0. So I'll take R3 minus 4R1. And what do I get? I get 0. And then I get minus 3. I get minus 4. Then I get 0, minus 4, 1. Please check my step if it is correct. And then what I'll do next is I'll keep the pivot here and then the pivot here. So I need to make this 0 again. So take R3 plus 3R2, 103. So what do I get? Well, I get 0, 0, 2, and then 3 minus 4, 1. Okay. And then what do I do next? So will scale the R3. Please check my step if I'm correct. If I'm correct or wrong. So 2 minus 2 and 1. Okay. And then the last step is to make these two 0. So we combine. So I do R1 minus 3R3, R2 minus 2R3. I get 1, 0, 0. And then what I get? Minus 9 over 2. And then 7 minus 3 over 2. 0, 1, 0. Then what I get? Minus 3. What's the next one? Plus 4. And then minus 1. 0, 0, 1. So the claim is this part here. Okay. So this part here is A inverse. Okay. So is this A inverse? Let's put these two side by side and see. Let's check our answer, okay? Let's do checking size. Okay, let's check. Okay. What's the first entry you get after multiplying? What's the first entry? So you take the first column time first row times the first column. What do you get? Minus 3 plus 3. Minus 3 plus 3. Something wrong again, is it? Okay. So please check something wrong here. First column, second row happened. Which one? Which one? Huh? -2, huh? Okay. Other than that, don't know yet. Okay, never mind. Let's check. So -1 plus 3. Okay, right here is 1. Correct? Okay. Can everyone see or not? Okay. This multiplication here. -2 plus 3. And then how about this and this? So basically we can ignore the first row, right? Because it's 0. Okay, so as long as here is 1 times second row plus 2 times the third row, then you should be fine. So my 1 times 4 plus -2 times 2 is 0. Okay, good. -1 plus 1, 0 again. Okay, good. And then how about here? 103. So -9/2. Okay, basically we can ignore the second row again. So 3 times 3 is 9. So -9/2 plus 9/2 is 0. Okay. 7 minus 6, 1. -3/2 plus 3/2, 0. Okay, good. How about the last one? So last one is a bit tedious. Let me write out. 6 plus 8/2. Okay, sorry. I put the wrong thing. So the first one is -4 9/2, 6. 8 times 3/2. Okay, which is 12. And then minus 2. So -18 plus 6 plus 12 is 0. Okay. And then how about let me move. Okay, how about the second one? 4 times 7 plus -3 times 4 plus 8 times -2. What do you get? 28 minus 12 minus 16 is 0. Again, good. So last one, you have to hope that it is 1. So 3 times -3/2. -3 times -1 plus 8 times 1/2. So you got 4 here, and then you got 2 here. So it's equal to -6 plus 3 plus 4, which is 1. Okay. Okay. So the story is, if you set this A/identity up, the large matrix here, Okay, and then you row reduct the original matrix to identity. Okay, and then you do the same operation on the identity matrix, and then what you will get on the right is the inverse. Okay. What's the times now? Okay, 3, 4, 5. There's another example here. So let's do it together. You do your own, I do my own. See who can finish first. Okay, and then see who get the answer. Let's spend about 5 minutes to do this. Everyone copy down this matrix already. Let me know if you found it. Okay. Can anyone manage to find the inverse? Manage to find the inverse? Anyone? Anyone manage to find the inverse? Has anyone managed to find the inverse? Heaven, heaven. No or heaven? No, cannot find. Okay. Say again. Doesn't have an inverse. Okay. Doesn't have an what's your name? Oh, Jinghao. Okay, okay. I'm Jinghao. Yeah. Okay. Yes. So this matrix actually doesn't have an inverse. So I think you should start at one place where you have a row of zeros. Okay. So this matrix is not row equivalent to an identity matrix. So it is not invertible. Not invertible meaning there's no inverse. Okay. So there's no inverse here. Okay. Because it's not row equivalent to not row. Okay. So it is. So A is not invertible. A is not row equivalent to identity matrix. So A is not invertible. Okay. So anyone still don't know what row equivalent is? So row equivalent means you can apply the three operation, elementary row operations. Okay, replace, scale, or interchange. Okay, if you apply these three, the result after applying these three, the matrix are row equivalent. Okay. Yeah. So you cannot find the inverse. Okay. If you manage to find one, maybe you have some calculation mistake. Okay. Any question up to this part here? No? If no, let's break until 4 o'clock and then we will continue to the next part. Yeah.
就上一个，就这个，
OK，
就是哎，就这个是你写的吗？
这个，
就是我们这里把 R1 和 R2换了一下嘛，就是这个忘记了。
identity matrix。
对 identity matrix 它不就变成了第一个是000，第二个是100，这个不影响吗？就是它最标准的形态不是这个吗？但是我们然后我们这边是符合定义了嘛？然后这两个它顺序换了，它就不是最标准的形。
哦，没有啊，没有，就是这个是我们的第一个步骤嘛，就是你每一个步骤作用在它，你都要作用在它身上。
就是说它只要一开始是标准就好了，然后后面是怎么样的变化？
后面那个是你要逐渐找到这个 A 的。
就是说后面它的这个顺序，这边的顺序变了也没关系。
它就是在寻找 A inverse 的当中，它就是会变。
OK，
明白？它不变，它就找不到它。
我知道，就是我之前做的都是它数字可以变，但是它这个 identity 它永远都是长成这个样子。
哦，对，这个是其中一个步骤是合理的，是可以变的。那3个步骤都是合理的。OK，
谢谢。
你叫什么？
我蒋欣怡。
蒋欣怡。
我学了3节课。
哦，你是那个生病了吗？
哦，不是，我是本来想去107请假的，然后他们说我要先打一张单子去他们那里盖章，然后我又把那张单子拿来给你签字，然后我把你签字的单子交到107，我才可以请。
所以呢？
所以说我就干脆不请了。
OK，
就是因为我会嘛，然后我数学率我算了一下，正好是80%，然后我就
OK， 好的，可以。前几个礼拜也没那么严重，因为人家也还在换榜。对，
谢谢老师。
OK， 好，太远了。
我就是刚刚最后一次。这一步
的出工具。
我知道他没有。
OK，
不是说解这个，就是说在比如说第2行和第3，
对，
判断它也不是刚刚讲，上一章不是讲它有没有那个，就是有没有点。
对，
就是我在处理这个时候，到底是拿它减去它，还是直接把它除以2，然后得到一个这两个不相等的话，你证明它分类。
再来一次。
就是我想想
啊
就是第2页
啊
就是我们看它有没有就是这3个未知量有没有固定起来的东西。然后我处理的时候不是3行减2个
，OK
2，
好
然后你得到一个第3行是000，
，OK
后面有后面有质量。
OK 好，
然后我就是如果是把3行直接除以2的话，然后就是你看后面这2个不相等的话，也能说明是没有固定。
你在说这一题还是你在
不是
说其他的？
其他的就是
其他的
但
，OK OK。哦，
那个叫增量
增量
matrix。
说，你看到这个东西的时候呢，
对
然后你看到这2个长得不一样，
对，右边
你说能不能直接从这里直接推？它没答案的。
对，他是说必须要得一个000后面有一个数点。
但是这个没有答案，也是因为那一个。
但是我们如果把它写回它的代数形式的话，
然后
它就是得到就是3x2加5，就是相当于
你说6等于7哈？
对，这样
也是可以。你那样子写你那样子写出来，但是我觉得你写来写去也差不多一样啊，对吧？是。对，也可以那样子写，
但是
也可以那样子写。
那个减一下，不就是刚刚说的那个000等于？
是，可以是一样的，就是6不等于7哦。我另外一个是0不等于1吗？所以6不等于7，0不等于1，差不多啊。
请问一下，这个算是 consistent 吗？
算，
然后这个才是 inconsistent。小声。刚才老师问一下，这个情况是
这样
inconsistent 啊。
inconsistent 对，
对，
没错。我给的例子还是你自己认识的？总的OK，所以这个的意思是说，OK，很直接。我有先看到。对，给我看看啊，the columns of the standard matrix，所以这个东西是从Rn 去 Rm，所以这个是一个 m 乘 n 的 matrix。OK，R the image of the column of the E 乘 E，OK，好，这个的意思是说什么呢？这个意思是说你要拿 A 去作用在这个1001这些啦，identity matrix 上面，OK，然后他说是不是作用在这边得到的这个 A，是吗？the column，所以意思是说你把 A 拆成 A1 到 A m 乘 n 个。OK，所以你是不是拿 A 去乘 identity matrix 过后，你会得到 A1 A，对吗？他的问题是这个。The columns of the center matrix, the column of the center matrix are the image of the column of the m 乘 n identity matrix。所以 image 是什么意思？image 就是说你拿你的 matrix 去 add on 这个 identity matrix 的 column 得到的东西，所以你拿去 add 得到的东西，是不是它？是吗？是哦，
对吧？
是哦，对。
会不会不是 free 的只有那种三个零在？那种就是只能加一个是
没有3个0啊，你看，这样也可以啊，01也可以啊。哈，
它是 free
那个是 inconsistent
啊，这样就不能讲
啊，连 consistent 都没有，你还不要讲 free 先，没有 free 好讲，现在这个不成立这些东西，这个 system 这样
就是可以调到刚刚那个 until 那里吗？
onto
说之前
这里
，OK，
哎，
在之前，
对，这里，就是不是说 onto 的话，这边还可以有一个，就是一个元素，然后是
相同的地方。
对，就是它如果这里有个元素，然后这边没有，
这边有个元素，这边没有。
对，就是比如说我，
你说没有一个箭头过去，
对，
不可以，
不可以，
因为每一个东西你都要知道送去哪里，所以呀，对，所以不存在没有被送过去的东西。
那如果我，
这
比如说我这
是方向。
边有个零，
对
然后我这边可以有好几个，就是我一个零可以对好几个选项这种，就是像这样的地方。
啊，对，
哦，
对，
那还有就是，
嗯
像刚刚那个，就我刚刚问的那个，
啊，
跑哪儿去了？
那个，
哎，就是这个
啊，
在哪儿啊？就我可不可以先把这个周 R1和 R2我互换了之后，我再对它进行一个 identity，我再给它写成一个 identity matrix，然后我再进行计算。
哦，不可以，因为你把原本的那个 matrix 换了。
哦，就是我必须要先 identity 了，我才能换。如果我要求它的反函数反
inverse，
矩阵的话，OK，
为什么一直纠结这个？
因为我觉得很有
它是
点怪，
正常的，
有点怪。
它是正常，它是正常，
OK
它是正常。
OK，谢谢老师。
你如果真的不要换它，不是，你也可以把 R1加 R2也可以，也可以。如果你不要交换了，I 加 R 也可以，那个 pivot 就跑进去啊。
是的，
嗯
对，那算下来还是一模一样的。
啊，但是不要太纠结了。
颅内运算的，因为我感觉提前换了之后，它这个矩阵不是说还是原来的矩阵吗？
不是，不一样的，不一样的，不一样的。哦，它是一样的解，但是矩阵不一样。
就是我给这个矩阵求解的时候，我可以先换，但是我给这个矩阵求 invert，
没有，我这3步骤不是它的解都是一模一样，矩阵不一样，但是它解是一样。
哦，那就是我也可以先换再那，反正它都是一样的解。
但是我要求的 matrix 的 inverse 它不是你换过的那一个。
哦，就是我这样的话就不太严谨了。但是
不然严谨是错的，
但答案是一模
不一样。你可以试下，我是说解是一样，但是 matrix 不一样。解是一样，跟 matrix 不一样的概念不一样，就是解的概念跟 matrix 都不同。
我好像理解了。
啊，matrix 可以不同，但是可以有相同解。
好，谢谢老师。
OK，
我很短，对吧？这个你可以算它是一个就是不是有一个定理嘛？就是如果说你是omp的话，那你就是每一行都有个 pivot position
啊，对，
那你这个都是零的话，它就没有 pivot position，所以它就不能红。
对，
那就这种零的
对 ，OK， 对 ，OK。好了，1.9。
1.9之前不是说考到10。
都完。
这个为什么一 P 跟API 就是那个
OK， 等一下
证明
，OK，能证明吗？
就是它进那个是 identity matrix。
啊，等一下，给我开始先。OK， OK， OK，Hello， testing，OK， Okay. So if you have more question, right? Okay, third hour. Okay, let's deal together in front of the class so that everyone can see the question and then see the answer. Otherwise, everyone asks the same question. Okay, so all the questions later we leave to the third hour and then we will discuss again. Okay, ask in front of the question so that everyone will know everyone will hear it. Okay, so I will pass the attendance sheet down now. So if you are new, right, please put down your name yourself, okay? Because this is all attendance list. And some name learning, because you email to me, right? But I don't know who are you. Okay, so it's a bit weird. So I want to know who is Sun Kailu. Oh, Sun Kailu. Okay. How about Luo Qingrui? Luo Qingrui. Okay. Okay. Then next time I'll learn more name. Okay. Okay. I think I know you have a lot of questions about one-to-one, on-to, and finding verse, but keep to the third hour. I will answer it. Okay, together in front of the class so everyone can hear it. Okay. Next part is a bit change of flavor. Okay. So change of flavor here. So we will look at a subspace of Rn. Okay. What's the subspace is? So the definition here is it is a subset. Okay. Subset of Rn. Okay. So what's the subset is? Okay. So for example, inside this class here, you got this many of students. Okay. If I take 3 of you out, these 3 students will become a subset of this set of students in the class. Okay, subset. So you pick. So imagine. How should we imagine? So let me draw something. Okay. So you have, for example, x1, x2, x3, x4, xy. You give them some name, and then I pick maybe 3 of them out. Okay. And this is a subset. Subset. Okay. But subspace is a bit more than this. Okay. There's condition on what we want to pick. Okay. So there are 3 conditions. Okay. Subspace have 3 conditions. So 1, 0 have to be inside your subspace. Okay. You must contain 0 inside your subspace. Second is for any 2 elements you have, if you add them up, it is still inside there. Okay. So this is what we call close under vector addition. And then third is you take any scalar, multiply to your element, it is still in there. Okay, this is close under scalar multiplication. Okay, so remember this is the only 2 operations we have on vector. Okay, with an extra condition, 0 must be in there. Okay, why 0 must be in there is quite obvious, right? If you have a vector, okay, 0 is a scalar. So you multiply 0 to the vector, you get 0 vector. So automatically from the third one, you can get the first property here. Okay, implies taking C equal to 0. Okay. So geometry, what in geometry sense, what is this doing? So let's look at R2 maybe. Okay. What's the subspace of R2? Okay. If I pick this is not a subspace of R2. Do you know why? You know why that line is not a subspace of R2? No? How about the others? Any idea? If I pick this line in R2, why is this not a subspace of R2? So meaning there's one of them is not satisfied, right? Which one of them is not satisfied? Huh? The 0 vector is not in the line. Okay, because the 0 vector is here. Okay, so it's not on the line. So it's not a subspace. Okay, so every subspace in R2 must pass by this origin. Okay, makes sense. Okay. Zero vector is a point. Yes. 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 Zero vector is a point. Yeah. Yeah. Later we will learn how to find the length of a vector, and then we will see that the length of the zero vector is actually 0. So which is a point. Yeah. This is later. Yeah. Zero vector is a point. Yep. Cool. Yep. Okay. Good. Any other question? No. Okay. 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 Let's stop here first, and then we will see more example in the tutorial and so on. Okay. Next example is if you this construction is what we learned last week. So you take a set of vectors, okay, and then you consider the span of the vectors. Or what's the span of the vectors mean? Anyone can recall it? What's the span of a vector? A set of vector. Meaning you can take the any linear combination of the so this is the only two operation you know how to do, right? For all C1 up to CP in R scalar. For all scalar. Maybe use something easier. For all scalars. Okay. Recall this definition here. Span of a set of vectors is a linear combination, is set of all linear combination of the vectors, right? Any objection to this definition? No? Okay. So why does this definition here satisfy the definition of a subspace? Okay. So first of all, if you multiply the vector by a scalar, okay, and you add the vectors together, do you still live in Rn? Is this vector still a Rn vector? Yes or no? Huh? Yes or no? Okay, okay. Okay, let me step back a bit. Okay, so example. Okay, let me look at R2 for example. Right, if you take a vector in R2, and you do some scalar multiplication, okay, and then you add to some R2 vectors, is this still in R2? Yes or no? Yes, right? Huh? Yes or no? What's this vector actually? What's this vector? Can everyone see or not? Too small. What's this vector? What's this vector? Can you calculate this? Cannot understand my question over. 8, 1, right? Okay. Okay, so 8, 1. 8, 1, is it a vector in R2? Yeah, right. Okay. So if you do scalar multiplication on the vector and then you do vector addition, you still stay in the same space. Okay. So first first the span is a subset of Rn. Okay. So this is the first condition you need a subspace before the 3 condition. What should I use? Maybe I use highlighter. So this is a subset, okay? And then you need to satisfy 3 more conditions, okay? Is 0 in the span? Is 0 in the span or not? Yes. Why? Why? Y0 is in the span. Let me move. Y0 is in the span. Huh? Wang Ye. Y0 is in the span. Oh. Okay. With vectors. Okay. So you can pick. You can pick all the scalars to be 0. Pick all Ci equals to 0. Okay. Then you will see that then 0 is in the span. 1 up to V2 up to. Okay. So why is it closed under vector addition? Because if you take any two vectors here, okay, maybe I need to show you the full thing here. Okay. Should I do it rigorously? Are you guys okay to see it in full? Okay. Okay, so take two V and W in the span of V1 up to V was VP. Okay. So by definition, what is this? So V can be written as a scalar multiple of Vi to Vp. Okay, for some scalars. V1 up to Cp. And W bar, you can write it in terms of another scalar, another set of scalar. Okay, we don't know what is it. Depends. Okay. So the question is, if you add them together, is it still in the form of linear combination of V1 up to Vp? What do you think? What do you think? Consider V plus W. Okay, what's V plus W? Okay, so you add out this bunch of vectors with another bunch of vectors. Okay, what do you get? Can you do factorization? Okay, so you factorize C1 and D1. Similarly for the other terms. Vp. Right. Okay. So now you write it in terms of a linear combination of V1 up to Vp again. Okay, because C1 plus D1 is another scalar. Right. Okay. So V1 V plus W is a linear combination of V1 up to Vp. So V plus W is in the span of V1. Okay. Okay. Any question from the back? Make sense or not? Okay. Okay. Similarly, you can imagine for the close under addition, what do you get? So if you consider CV, what do you get? You will get C times C1 V1 up to C times CV. So it's still a linear combination. Okay. So try and work this out. Try work this out. see yourself. Okay, I will put it in the lecture note later, but you can try and see it. If you multiply C to any vector, it's still a linear combination of V1 up to Vp. Okay. Any question? No? Okay. Okay, next. Next is a column space. Okay. So a column space of a matrix is also a set of linear combination. Okay, linear combination of what? Okay, of the columns of A. Okay, so it's denoted by col A. Okay, so this means you have a matrix. You have a matrix. You split them into columns vector. I think this is quite familiar to you now, hopefully. Okay, so you consider the linear combination of the columns, right? So you have, for example, like x1 plus x2 times a2 plus up to Sn times an. Okay? So you consider set of all linear combination of the columns. Okay, and then show that this is a subspace of Rm. Okay, you know how to show? It's the same. It's the same. Same way how to show the span of n vectors is a subspace. You just change it to a column vector in your matrix. Okay, it's literally the same proof. Okay, this is the same as how you show n of a1. Okay, you can try and work it out how to show. Okay, it's the same as what we did just now. You just change the vectors to some column vectors in your matrix. Okay. Okay. So let's look at one example here. So example here, you got a matrix, a real matrix, 3 by 3 matrix, and then B, your constant matrix, constant vectors, a solution. Determine whether B is in the column space of A. Okay. So this means that whether B is a linear combination of the columns of A or not. Right. Whether B is a linear combination of A or not. Okay. So this means that B is a linear combination of columns of A if and only if the vector can be written as the matrix kind of vector. Okay, because you can get the B from there's a solution such that you multiply A, you get B. Okay, so the question is equivalent to find X such that AX equal to B. Okay, because B is a linear combination of columns A is what? The vector equation, right? Remember the vector equation. So x1 x1 a1 plus x2 a2 plus x3 a3 equal to B. Okay, this one is equivalent to AX equal to B. So what you do is you need to make an augmented matrix and then row reduce it. If it is consistent, that means it is in the column space of A. If it is inconsistent, then it is not in the column space of A. Okay. You want to do or skip? Want to try and do or skip? Try and do. Okay, try and work out whether B is in the column space of A or not. Anyone have done the calculation? Okay. Anyone do up to this step already? Anyone do up to this step already? Anyone? This already? Okay. Okay, basically you can stop here. Okay. Actually, you can stop here already. Okay. Because you can see that there's two pivot column here. Okay, there's two pivot columns, right? Okay. And then this system is consistent. Okay. Consistent meaning what? There's one or more than one. Okay. But in this case, you have more than one because S3 is 3. Okay, so there's a solution to this. So B is in the column space of A. If the question say, write B as a linear combination of a column space, write B as a linear combination of the column vectors, then you need to solve this augmented matrix to find what is S1, S2, S3. Okay, if not, you don't need to solve all the way to row reduced echelon form. Okay, get it? Don't waste your time to do unnecessary calculation. So up to here is enough to see that there's a solution to this system, and then B is in the column space of it. Okay, everyone okay that we can stop here and then can read the answer? Okay, no need to do unnecessary calculation. Okay, you don't need to compute to the end unless you want to get the exact solution. Okay. Okay. Next, row space. So just now we look at matrix vertically, right, in the column manner. Now we look at the matrix as a row manner. Okay. So row space of a M times N matrix A is a set of all linear combinations of the rows of A. Okay, row space. So instead, you take the column vector, now you take a row vector. Okay, that's it. Why is it a subspace? Because you still consider linear combination of a set of vectors. Okay, so you can use the same method to prove. Okay, the next part is a bit interesting. So the null space, okay, null is 0. So what's 0 about this space here? So the null space of a M times N matrix is the set of things, okay, maybe non-zero, but it get mapped to 0 by A. Okay, this is the null space. Okay, it's the space that make your matrix null. Okay, so after you apply your matrix, you get 0. Not necessarily 0, but so X may be not 0, but AX must be 0. Okay, so this is called null space. Null space is not nothing. It's the thing that When you apply A, you get 0 vector. Okay, null space. So why is it null space a subspace? This is a bit interesting. Let's look at it. So first of all, why null space is a subspace of is a subset of Rn. Why null A is a subset of Rn? Anyone know? Why is it null A a subset of Rn? Huh? Vector 0? Not yet. Haven't zero vector yet. So why null A is a subset of Rn? Okay. Why the element in null A? Does everyone know that this notation here? In, okay, in null A is in, okay, y, then x is in, right? Anyone know why? A add on what space? What's the size of A? Huh? What's the size of A? What's the size of A in this case? Size. M by N, okay? So A is a N, M by N, okay? So you add on what vector? What kind of vector you add on? N by 1, okay? So you add on Rn, okay? So the vector you take should be Rn. Okay? Yeah, okay. Then since A is a N by N matrix, okay? Right? Everyone follow? Okay. Okay. So how about next part? Y0 is in the null space. Why? Y0 vector is in the null space. Huh? Why? Yeah, I use the same matrix here. Okay. Why? Y0 is in the null space. Okay. To be in the null space, what equation you need to satisfy? A, the matrix add on the vector, you get 0. Okay, right? So if you take a matrix and add on the 0 vector, what do you get? 0. Okay. Because A add on 0, you get 0. Okay. So if you really want to know what I'm doing here, you should spread this 2 0 here. So this 0 is coming from here. The other 0 is coming from the null space definition. Okay. 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 So because it satisfies this equation here, so it is in the set. Okay. To be in the set, you need to satisfy this equation here. Okay. Okay, next. Okay, next. So if you take two elements from the set, why the sum of them is in the set? Okay. So why the sum of them is in the set? So let me move things away. Besides. Okay. So the third part, the second part is suppose x and y is in the null A. Okay. Then x plus y is in null A. Okay. So to show x plus y is in the null A, what do? You need to check the condition, right? You need to check the condition. So A apply on x plus y, what do you get? What do you get? Distribute ax plus ay. Okay. So what is ax and ay respectively? Why? Why are they 0? Because I suppose that these two vectors are in the null space of A. Okay, so separately they are 0. So 0 vector plus 0 vector, what do you get? 0. Okay, so AS plus Y is in the null space. Okay, similarly, you can do it for the scalar multiplication part. Suppose S is in the null A, then CX is in null A. Okay, so you take A, apply on CX again. What do you get? What do you get? Can you bring A closer to X? What can you do? What can you do? You can take the C out. Okay, and then do this. And then you get C times 0. Which you get 0 again. Okay. Any question? No? Okay. All good? Okay. This one is 1, 2, 3, 4. Okay. Please just stop me anytime if you have question. Because maybe you don't think about it, but suddenly you think about it. Just stop me anytime. Okay. And then the next part is, what time is it? 4, 3, 8. Okay. So the next part is basis. Okay. So what's the basis? If you have a linearly independent set, okay, and expands, so you have two conditions together, it will form a basis. Okay. So it will form a basis. So you must be linearly independent and then span the set, span the H, span the subset H. Okay. Okay. So for example, okay, last time we introduced this standard basis of Rn. Okay, what is EI? So I remind you again, what is EI? So EI is the thing that is 0 at the I spot. Okay. So for example, E1 is 1, 0, 0, 0, and then E2 is 0, 1, 0 all the way. And then EN is the 1 at the last spot. Okay. So EI is the that has 1. And then last time we talked about their name, standard basis, but we haven't really see why is it a basis. So the claim is this set of bases is a linearly independent set in Rn, and they span Rn. Okay, let's see why is this true. Okay. So remember, what's the definition of linearly independent? You need to set out the vector equation. Okay, so what's the vector equation? Let me throw this thing away. Okay, so linearly independent. So first, they are linearly independent. They are. Okay, so linearly independent means for C1, E1 plus C2, E2 plus dot 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 up to Cn equal to 0, we must have the what kind of solution? Only what solution? Trivial solution. Okay. That is what? CIR 0 equal to dot 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 equal to Cn equal to 0. Okay. So to solve this vector equation, what do we do again? What do we do? Vector equation is equivalent to a matrix equation. A matrix equation is equivalent to an augmented matrix. Okay, so what's the augmented matrix here? So 1, 0, 0, 0, and 0, 1, all the way down. Okay, let's do for maybe R3, okay, example. If you want, you can write for general case, but just look at R3. Every case is the same, 0, 0 again. Okay, so what solution do you have for this augmented matrix? What solution do you have? Can read solution from this augmented matrix here. Is this a reduced raw echelon form? Yes, right. So you can directly read solution from here. So what's x1, s2, s3 you get? 0. Okay. So what do you observe here? Yeah, what do you observe here? So you have a pivot column. You have pivot on every row. Okay, and also every column. Okay, so you have only one unique solution. Any question? No. Yeah. Okay. So this observation here. Okay, let me write down this observation. Observation. You have a pivot at every row and every column. Then you have a unique solution. In this case, when you solve for the homogeneous equation, you get 0. Okay, homogeneous system, you get 0. Okay, how about span? How about span? About span? Okay, span. Span. And let me resize it. Okay, how about span? So span mean what? For every B in the Rn, okay, you can write it as a B is a linear combination of E1 up to En. Some scalars C1 up to Cn. Okay, so the question is like changing the 0 to arbitrary B, any B. Okay, any B. So the augmented matrix is like changing from, so this one is just example. To not confuse you, maybe I use green. So so the example here should be generalized to arbitrary n. All n the same argument. So let's look at the same example here. So you got B1, B2, and B3. Okay. So what do you observe here? Do you have a solution? Do you have a solution? Yes, right. Okay. Really, you just set your variable to the entry in the your constant vector. So why is this standard? Because you have an easy, unique solution to this vector equation here. Okay, so that they are standard. You just read out the first entry, second entry, third entry, fourth entry, and then so on. So these are the standard bases. So we can have different bases of Rn. Then in that case, this number here will change. Sorry. Where is it? Okay. So if you have a different basis here, okay, then the solution will change. Yeah. These are standard because when you solve for this augmented matrix here, what solution you will get is exactly the entries of your vectors. If you change to different bases, then the solution is not that easy. Okay, not that straightforward. Not easy, but not straightforward. Okay. Yeah. Okay. Okay. Okay, how about find the basis? Let me see what time is it now. Let me see. Okay, okay, let us finish this question and then we will take a break. Okay, let's finish this question here. We'll take a break. Okay, now we want to find the basis of a null space. Okay, so null space means what? The solution that multiply to the matrix, you get 0. Okay, so what you do is you solve it for the augmented matrix. So this is the equivalent to solving the augmented matrix 6 minus 2 minus 4. The homogeneous system attached to this matrix. Okay. Okay. Can someone raw reduce this? Try raw reduce this. Okay, I will raw reduce with you together. Okay. Let's do together. Okay. How to raw reduce this? Let's raw reduce together. So whatever we do, right, you'll notice that we are keep raw reducing stuff. Just that we give different answer, give different interpretation to the answer. So this means that raw reducing is a very important skill in this course. But to know what augmented matrix to reduce is also very important. So make sure you know how to read the question. Usually, right, they give the augmented matrix should be very nice to raw reduce one. So there should be a nice calculation usually. Okay, in this case, it turns out to be quite nice. If you think it is nice, then you are most likely on the right track. Anyone have done it? Please check if I'm the same. If we are the same answer. Okay, after you raw reduce it, try to write your answer in terms of parametric vector form. Write it in terms of parametric vectors form. So this is count as the tutorial time. So tutorial time are sparse between a lecture time instead of one chunk. Because there's only one lecture here. There's no other tutorial. Lead up. Initiate. Anyone got this answer? Anyone got this answer yet? Anyone got the same answer with me? Huh? Anyone got it? No yet? Last part? Last part. Oh yeah, last part. Okay. Yep, correct. This one is free, so you got one here. Okay. Calculating or not? Got the same answer? Okay, so we got this answer here. So what does this answer do? Okay, what does this answer mean? This means that if you apply the matrix to this solution, you get what constant vector B you get? You get? What do you get? What do you get? If you apply A to X, what do you get? You get? What's the system you solve for homogeneous? So what do you get? 0. Yes. Okay. So these are precisely the vector in the now space of A. Okay. Because it satisfies AX equals 0. Okay. So this equation says that every X in now A, X is a linear combination of the three vectors. The three vectors, namely 2, 1. Okay, let's move 2, 1, 0, 0. And then, okay, I'm writing smaller and smaller. Let's move everything over. Copy. Okay, so this means what? So every X is a linear combination of the three vector written down here. Namely 2, 1, 0, 0. And then 1, 0 minus 2, 1, 0. And then minus 3, 0, 2, 0, 1. Okay, this means that this three vector. Okay, let me rewrite everything properly. So AX equals 0, and then X implies is in the null space of A, and then Then we have this equation here. So we have a description of explicit description here. So let's move this up. Size. Okay, so this means what? This implies that every x in now A is a linear combination of the three vector here. Because every x can be expressed as a linear combination of the three vectors here. Okay. In particular, they. Okay. Do you know who I refer to if I put they? Just copy. In particular, these three vectors here span now A. Okay. By definition. Okay. Okay. To be a basis, you need to span. You also need to show that it is linearly independent. Okay. So why these three vectors here linearly independent? So what do you have to solve for linearly independent? Trivial. Okay. So let them equal to 0, right? So you need to solve the vector equation where this part is equal to 0. So you need to solve this thing equal to 0. Let's make it shorter. So you need to show that this part here equal to 0 or trivial x2, x4, x5. Okay. To show that there's three. Can anyone see why only trivial solution can solve this vector equation here? Anyone see why? Anyone see why? Actually, there's some specialties about this calculation, right? Remember, these are found using the pivot column. Okay. So you can see that there's one appearing on the fourth entry here, but other is 0. And then for the fifth, you can see that only one can generate this part here. Okay. So if you want to make the fourth entry, okay, this one a bit short. 1, 2, 4, 5. So if you want to make the fourth and fifth entry into 0, you can only make S4 equal to 0. Okay. Similarly, if you want to make S5 equal to 0, you can only have S5 equal to 0. For the fifth entry to be 0, sorry. So these two parts have to be 0. Okay. If this 2 is 0, how to make this vector into 0? X2 have to be 0 as well. Okay. So in this case, only S2, S4, S5 equals 0 will solve this vector equation here. Okay. Okay. Yeah. So this is something special about the spanning vector from the null space, because this free variable part here will force the coefficient to be 0. And this is true for general, where you can check for different exercises. Okay. Any question? Any question about this? Any question? So in the real how's it? I think the real exercise, you just need to solve up to here. Okay, you need to solve out to here and then tell us that who is the basis, who is in the basis. Okay, so in this case, you will say that in this case, let me show you the real solution first. So in this case, 2100 10 minus 210, and then 3201 forms a basis for straight away from here. So the down part here is to explain why it is true. Okay, you don't need to show, but you just need to understand why it is true. Okay, practically, after you solve the parametric vector form, after you get the parametric vector form for the solution, then you can deduce that the vectors form a basis for now. Okay. Any question or not? Any question? Any question for anyone? Any question? If not, let us break for until 5:05. Maybe we'll come back because someone need to leave earlier, so we have to stop on time 10 minutes before. So let's break until 5:05. Huh? Hey, sorry. 5:10. 5:10. Okay, 5:10. Sorry.
它能这么说，
怎么说？
就是你要从列去横去想，你去列去想这个东西，
嗯哼，
然后就是 C1的2倍的 C2 加 C5，它是等于 C3，然后上来就可以猜它，因为 C
哦，你猜的话
它之后列出来之后要证明，
，OK，你猜完了，然后呢？
猜完就是 C2 选一个，然后 C5、C3选一个，
但是你
再选一个 C4，
你怎么知道你已经？
然后把这个那个线性独立集写在这儿，然后再把它画成这个矩去证它这个矩阵它是不是 identity， 去证它是不是，把它画成最简，它确实是，所以它成立。
我以为你想干嘛现在？所以你先要
它成立了之后就是它这个点儿。
你说这个是你的 basis 啊？这个啊，
哦，对，
但是我的 basis 是一个 R5 的哦，它是一个 R5 的，它是存在于 R5 里面的东西。你这个只存在于 R3罢了。
相当于这句。
但是它记得吗？它的能够 null space 是活在R5里，它活在 R5里。
R5，
它的 null space 活在 R5里，不活在 R3里。
没听懂的样子。
你问一下，
先让人说。
OK，
就什么情况会算到不等于 vector 0？就我刚才前面那个，就它不是等于3个0，5个0那个3个0这边，这样有什么会不会有一个情况就是它 not equal to vector 0？
可以啊，
就这边会
可以啊，
不等于
可以啊，因为这个我们要 solve null space 嘛，所以 null space 的话一定是看这个 homogeneous system。
像它这里什么情况下才不会就会 not equal？
你想它
像
not equal，
像它这个是 equal 嘛？
对，
像它这边什么情况会 not equal？
哦，什么情况会 not equal？就是给我想一下啊， 就是你不要选这个 solution 给你的答案的时候，它就会 not equal。
什么意思啊？
就是意思是说，如果你把这个 vector 换掉，它就不是零了。比如说你把这个2换成1，
啊，
那你就去算一下这个11000的作用在上面是什么？这个就不是一个零的 vector，可以给到吗？可以给到，就是你把你的 solution 换一换
哦
啊，
哦，
你
要么就是我算错了啊，
算错
就好像如果算到这个1，
啊，
然后意思说我带回进去的时候就不能
就不会等于零了。
啊，
你把这个答案稍微改一点，它就不是。
笑死。所以总之是一定会等于0的。
因为是我们找的，是我们要的，你可以不要，是我们要的
笑死。
啊，因为我们要找 not。
所以
不一定啊，睇一定嘛，
不一定嘛。
叫啥？好像是，
为什么？
因为两个 vector 要 linearly dependent 的话，等于 v1一定要等于一个数乘 v2，OK，所以是说它一定是和 v1活在同一条线上，就是说你只能够延伸这个 v1或者反方向，它还在。
对，
啊这个哈，是因为你可以找到 example such that 这个是错的
看不懂这个题什么意思？
啊？
看不懂这个题什么意思？
哦，这个题什么意思？这个意思是什么意思？你可以借我笔吗？就是是说，比如说，所以你看这里的有2个 vector，但是它的 entry 有3个，所以是2小于3。然后要证明这个它也可以是 linearly dependent，听明白吗？给慢，
这个 space of an m by 2 matrix A，然后我解这个题的时候，我要确定这个 B 是不是这个 space of A，解到这里，然后它不是，它这个例子不是说它是是这个 linear combination，那我做到这个之后，我怎么判断它是不是 linear combination？
Because there's solution to the system。
就我可以解出来这个 x，
Yes。
可是我把 x 解出来之后怎么看？就怎么判？就是这个肯定可以把 x 解出来。
OK，不然，那你说 OK，没有了，没有。哎，OK， wait. Okay, I know you guys have a lot of questions, so one by one. So okay. So the first question is for this question here. Okay. Hey, where's the cat? Is the cat out? Okay. Okay, be careful with the cat because if you get scratched by the cat, you might need to have some vaccine. Yeah, need to do some injection. So please be careful with the cat. And okay, so one student asked about this question here. Okay, Joey asked about this question. So so you want to determine B as a linear combination of the column vectors of your matrix. So after you solve this augmented matrix, you found that you have a solution. Okay, so what does this, how does this answer the linear combination? Okay, what do you mean by you have a solution? Okay, solution to what? Solution to what? What equation here? Okay, so what's the solution here? So the solution here is exactly answering the vector equation limited space. So okay, so the solution of this is exactly answering the question saying that x1 times a1 plus x2 times a2 plus x3 times a3 equals to b. Okay, so this is the solution get from the augmented matrix. And what is this vector here? This equation here. This is exactly writing B as a linear combination of A1, A2, and A3. Okay. Okay. So yeah, although I haven't explicitly write down what is S1, S2, S3, but I know that there's at least one solution to it. So it's enough. Okay. So whenever you solve the augmented matrix, you need to know what equation you are solving. Okay. Don't just do the row reduction. Okay. Do you have a question from last hour? No, the guys behind you. You want to ask now? You okay? Okay. Sanqing, you got question? No? Okay, okay. Don't be shy, okay? Okay. Yeah. Okay. So this one, okay, done. Okay. Okay. How about finding basis for column space? Okay. So about finding basis for column space. So meaning that if you split your your matrix into column vectors, say B1, B2, B3, B4, and B5, okay? Can you write any of them in terms of linear combination of the others? Okay. For this case, can you do it? Can you try? Just try. We haven't seen, I don't know if it's true or not, but let's try. Can you write some of the vectors in terms of the other vectors? How about B3? Can you write B3 in terms of B1 and B2? Linear combination of B1 and B2. What is B3? B3 is minus 3 times B1 plus 2 times B2. Okay. Similarly, B4, you also can write some equation down, which is 5B1 minus B2. Okay. I think that's all. You can try, but that's all. Okay. So the claim is B1, B2, and B5 span, first of all, span the column space. Then, okay, I use the notation COL of A. And, okay, they span column A, Okay, because every vectors in the column space, you can write it as a linear combination of B1, B2, and B5. Okay, because B3 you can write in terms of B1 and B2. B4 you can also reduce to B1 and B2. Only B1, B2, and B5 stay. Okay, and then second, they are linearly independent. Can you see why they are linearly independent? Can you see why they are linearly independent? Huh? So if you solve the equation again, okay, so if you solve the equation again, C1 B1 plus C2 B2 plus C3 B5 equals 0 only as the preview solution. Okay. Is it easy to see why you have only trivial solution? Can you see why there's only trivial solution here? Can you see why? Huh? Why linearly independent? So one way to see it is to put it into the augmented matrix again. So you get 0, 1, 1, 1, 0, 1, 0, 0, and then 0, 0, 1, 0. Okay. Okay, so from here, what C1, C2, C3 you get? Okay. Okay. So what C1, C2, C3 you get for this augmented matrix here? You have pivot position in every column. Okay. So how many solutions you have? How many solutions you have? One. Okay. In particular, C1, C2, C3 are equal to 0. So we have only trivial solution. Okay. Yeah. Okay. So this one is for linearly independent column A. Okay. Actually, more rigorously, to see B1, B2, and B5 span column A. Okay. We need to consider any V in the column A. Okay. Such that E is a linear combination of the vectors in the column A. So it's C1 times B1 plus C2 B2 plus C3 plus times B3 plus C4 times B4 plus this one, get rid of it. E5 plus E4. Okay. And then you can use the identity we have here. Let us call it, maybe call it 2. Call it what? Z. Okay. Or maybe call it cat. Okay. So by cat. Okay. By cat, we can replace our B3 and B4. Okay. Replace B3 by minus 3 B1 plus 2 B2 plus C4 times 5 times B1 minus B2 5, B5. Okay. And then let me make it smaller and then we can make it larger. Smaller. Okay. So in the end, we get, if we collect the like term, what do we get? Minus 3C3 plus 5C4 plus B1 plus C2 plus 2C3 minus C4 B2. Okay, so you can see that every linear combination of your column A can be expressed only in terms of B1, B2, and B5. So this means that B1, B2, and B5 span the columns of A. Okay, so this is a rigorous way to see it, but it boils down to whether you can express this single column vector as the others. Okay. Any question? Any question? No? Any question? Huh? No question? No? Okay. Okay, so this one is the span. This one is a linear independent, so two parts here. Okay. So similarly in exam, what you do, okay, observation here. So what you do in the exam? Observation. Anyone make some observation here? What does B1, B2, and B5 share? What properties does they share? So, what do they share? So B1, B2, and B5, what property they share? Yeah, what property they share? I wish I know cat language. So what they share? What kind of property they share? What kind of property they share? B1, B2, and B5? Huh? Pivots, yes. So observation that, okay, B1, B2, and B5 are pivot columns. Okay. So the pivot columns will be the basis of your column space. It's a span your column space and they form a linearly independent set. Okay. Yeah. So your pivot columns, they form a basis. Okay. Okay. And okay. How about row space? Okay, so there's two parts of it. So one is a column space, one is a row space. Okay. So row space you need to see like this. Okay, horizontally. Horizontally. Okay. So you can see that these three vectors are linearly independent to each other. Okay. Because you can see that there's like one at the various spot. Okay. So because to make first entry 0, there's only way you can make this 0 is to multiply 0 to the first row vectors. And then to make second entry 0, the only way is to multiply 0 to the second vectors. And then similarly, you need to make this 0 by multiplying 0. Okay, so there's only one trivial solution to the linear independence vector equation. Okay, so they are linearly independent. Third, they span, automatically they span. Okay, definitely they span because you are looking at the span of these vectors here. Okay, so how should I name them? So what name do you want? So put W1, W2, W3, W4. So W1, W2, W3. Basis of the row space of it. Okay. So I challenge you. So I challenge you to write down the so I put a homework here. So homework is this one not very visible. So let me put okay, so homework here. Try I will also write out a version you can try out on yourself. So homework is to the homework is to show W1, W2, and W3 span row A. How? May calm down. Oh, you need to, yeah. Maybe you go away, then let the cat jump down. Careful, careful. Bring the cat out. Hey, bring here. Bring the cat out. Bring the cat out. Bring it here. Oh. Yeah, say bye to the cat. Bye. Bye. Okay, so homework is to show W1, W2, W3 span row A, and they are linearly independent. Using the same method, we show it for the column A. Okay. Dependent, independent. I'll write out a version and then we can compare. So try and do yourself first. If you are stuck, never mind. At least you will try. Okay. Okay. Next is this part here. Okay. So I will straight away see what happened. I will straight away tell you what happened here. So if you try, okay, homework, you can go and row reduce it. So I'll try and row reduce this. Row reduce. What you will get is the previous matrix here. Okay. You will get the previous matrix here. Sorry. So what's the previous matrix? So let me copy it down. So the row reduced form is this. It's exactly same matrix. Okay. So from here, how you read out the basis of the column space? You'll notice that the column space before and after actually change. Okay. Because you can see that there's non-zero entry in the fifth column here. Okay, but there's no non-zero entry in the fifth column here. So how you gonna use this vector here to produce non-zero entry here? Impossible. Cannot. Okay. So they are. So I will say that co A is not the same as co A prime. Okay. So after you row reduce, their column space change. Okay. But what doesn't change is the relation between the column doesn't change. Okay. So row operation do not change. Do not change the relation between columns. Okay. So this means that if you pick out the original column, which represent the pivot column here, they will span the original matrix here. So meaning what? Meaning the first from the RREF, we see that 1 minus 2, 2, 3, the first one, the first column vector, the second column vector, and the fifth column vector form a basis. We won't prove why row operation do not change the relation between columns. Change the relation between, yeah. But because it's a bit tedious to write it out, but I suggest you to try and think about it. Why row operation do not change the linear dependence relation between columns? Let's say you have a dependency between columns. Why, if you do row operation, it doesn't change the relation? If you get stuck, you can talk to me. Okay, if you get stuck, you can talk to me, but we won't do it here because it's a bit tedious. It's not too hard, but it's a bit tedious to write it out. Okay, so row operation do not change the linear dependency relation between columns. Okay, so from the row reduced echelon form, the original columns that represent the pivot column will become will form a basis of the original basis of the column space of original matrix. Okay. How about row space? Okay, how about row space? For row space, actually they are equivalent. So row space, this one is 1, this one is 2. So row space, actually they are equivalent. Okay. Because imagine what you do to the row. Row operation, what do you do to the row? You take the whole row and then you exchange with another row, or you take a linear combination of row. Okay. So you really doesn't change row A. Right? Because what you do in elementary, okay, let me write down. Elementary row operation. What does elementary row operation do? Row consists of linear combination of vectors in row A. Okay, because you take the whole row, you multiply, you scale it, and then you take the sum between rows. Okay, so this means you still live in the space of span of row vectors of it. Can you imagine this one? Wait, do you have a question? Look at me like that. You have a question? Any question? Okay. Can anyone understand what I wrote here? So elementary row operation consists of a linear combination of vectors in row A. Anyone is not understand this?
How?
Mm. Mm. Okay. I'll try to put this. It means what it means, but I'm not sure you can see or not. Okay, so what elementary? I think I spelled something wrong here. Okay, so recall what's row elementary row operation do. Okay, what do? You exchange vectors, right? You exchange vectors. Okay. Okay, let us study this line here. So what am I writing here? Copy. Okay, what am I writing here? Am I talking some nonsense here? Elementary row operation consists of linear combination of vectors in row A. So what do you do? So what can you do is your interchange. Okay. So you just interchange vectors. Okay. And then second, you scale vectors, scale row vectors. So if you scale the row vectors, after scaling, is it still in the linear combination of rows vectors? Yes or no? Yes, right. Because you okay. Like this. Okay. Okay, like this. Let you imagine something. Okay. So let us imagine a vector in your mind. Okay. We got 4 row vectors in your mind. Okay. R1, R2, R3, R4. I draw the line out. So 1 you interchange, 2 scale. Why is it a linear combination of R1, R2, R3, and R4? Because you can write it as 3 times R1 plus 0 times R2 plus 0 times R3 plus 0 times R4. Okay, so it's a scalar, it's a linear combination of the 4 row vectors. How about the, what's this? Replacement. Okay, replace. So for example, okay, these are examples only, okay? So for examples, row 1 minus 3R2, okay? How is this a linear combination of the 4 row vectors? You can write it as 1 times R1 minus 3 times R2 plus 0 times R3 plus 0 times R. Okay, so this is the set of scalar you can find to write it, to express it as a linear combination of the row vectors. Okay, is it clearer now? Is it clearer now? Okay, so elementary row operation consists of the different type of linear combination of vectors in row A. Okay, can I say different? Yeah, different. So different linear combination vectors in row. Okay. So yeah. So really, after row reduction, your row space is still the same. Okay. So you can really use this to be your basis. Yeah, it's quite surprising that one job you can find 2 things. Yeah, it's kind of surprising that just using row reduction, you can find the basis of core-A. You also can find the basis of row A. One stone can kill 2 birds. What? Okay, so 1 stone can kill 2 birds here. Okay, so the 2 birds here is basis of column space, and basis of row space, and then the stone is row reduction. Okay, so this stone is pretty powerful. You must know how to do it. Okay, so this warning I talked about it already, and then this theorem is the observation we did just now. Okay, the pivot. Okay, let me make it bigger. So the theorem says the pivot columns of a matrix A form a basis for the column space of A. Okay. Yeah, this one is the observation we made just now. And then I already show you how to prove this using an example. But for general cases, it's really the same argument here. Okay. 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 Okay, go to the next bit. Okay, next we'll talk about dimension and rank. Okay. So first is the coordinate. So coordinate of what? So suppose B is a basis for the subspace H. Okay. Then every X in your subspace can be written uniquely as some scalar multiplied by the vectors in the basis. Okay, and then we collect the scalar as a vector. Yeah, we collect the scalar as a vector, and then we call it the coordinate vectors. Okay. Okay, let's take an example here. Okay. I want to spend some time exploring this definition. Okay, so this important part we will do later. So let's look at example, right? So let's look at example. It says we start with a basis. So let's start with a basis. What basis we start? So let's pick something from R2, easier for calculation. Okay, so this thing is a subset of R2. Okay, and it forms a basis. So you need to show that it spans R2 and linearly independent. Okay, I left this as a homework. Try and do at home. Use what we have learned just now. Okay, and then say, since this is true for all x, right? So let us pick some vector. So let's say we pick x equals to, x equal to 2 minus 3. Okay, so 2 minus 3 can be written as, uniquely written as a linear combination of we actually have name for it, these two, right? E1 and E2. Okay, so what is C1 and C2? What's the scalar in front E1 and E2? And -3. Okay, so in this case, the coordinate vector of this x is 2 minus 3. Okay, so you see what's happening here. So we extract the coefficient again. Okay, this is what we did in the first class. We have a linear system, we extract the coefficient. Okay, now here is similar. We have a basis. Okay, then we extract the coefficient again. Okay, can see a lot. Okay, so this coordinate vector relative to B is the coefficient of the coefficient of x expressed in the expressed as a linear combination of vectors in the basis. Let's say, how about we change the basis? Okay, let's change the basis to 1, 0, and 1, 1. Okay. Okay, so same homework here. So show it spans R2 and they are linearly independent. So can you work out what is the coordinate vector for B in this basis? Can you try and work out? You can calculate using eyes by inspection, or you can use augmented matrix. Try and get what is the coordinate vector for this x under this new basis here. Yeah, I give you about 3 minutes maybe. Find the coordinate vector for this matrix, this vector here under the new basis. Yeah. Try and find what's the coordinate vector of x in this new base relative to this new basis. Yeah. Because there's only two arguments in your vectors, maybe you can guess, or you can work out some method to find it. Anyone have a guess? What's the coordinate vector? Or you are still calculating? What's the coordinate vector under relative to this new basis here? Huh? 5 and a 3. 5 and a 3. Minus 3. Okay. So one of you guess is a 5 and a minus 3. So let's see what's this telling us. Okay. So this one is the color. Okay. So one of you suggests that it is 5 minus 3. So what does this mean? So this means that x is equal to 5 times the first vector minus 3 times the second vectors in the basis. So you get 5 minus 3 and minus 3, which you get 2 minus 3. Yes. So how do you get it? Can you tell us how do you get it? Okay. Okay. You use the augmented matrix. Yes. Okay. So this is kind of a standard way to see this question. So since this is a linear combination of the two vectors in the basis, right? You can form the vector equation again. Okay. So what vector equation you can form? So you can form the vector equation again. That x is equal to x1 times the first vector in the basis plus x2 second vector in the basis. Okay. So from here, you are solving s1, s2 again. So you are solving the augmented matrix again. Okay. This is equivalent to solve 1, 0, 1, 1, and then you put your x here. So 2 minus 3. Okay. So this is a standard way to solve this question. Okay. Okay. So why? Okay, it's 5:50 now. Let me see. 1, 2, 3, 4. Okay, 3 more pages. We will continue tomorrow, and then tomorrow have a quiz. And any last question you want to ask before we end? Last question. Any last question you want to ask? Okay, no. Tomorrow we will continue with this coordinate vector again, and then we will have quiz tomorrow, and then good luck in your revision, and then we'll see you tomorrow early morning 8 o'clock. Hello. Quizzes until 1.9. 1.9. Finish the chapter 1.
没有机会。